So we're going to start with lecture number 8, and it is on Object-Oriented Databases, an introduction to object-oriented concept. It applies towards Oracle, but it's not. It's more generic than that. It applies towards object-oriented databases in general. It talks about object concepts and introduction to OODBMS systems that are object-oriented. So I'm going to talk about advances in database applications and things of that nature. And the unsuitability of the relational database model for advanced database applications, object-oriented concepts, problems of storing objects in relational databases, and the next generation of database systems. So this is kind of our concluding kind of lecture for our look at Oracle and databases for this course. Advanced database applications. So traditionally in the past, especially when we were working with relational database systems, we had database systems, that acted as a repository of data. We loaded data into it, we used data, the application is connected to the database, and it was primarily an object or a warehouse or something that was storing data. So nowadays we have more sophisticated applications. We have geographical information systems, GIS mapping programs, CAD systems, CAM systems, all sorts of different types of advanced kind of applications that are using a database concept that the relational database model doesn't necessarily meet the needs of. Relational database models are great as a hierarchy of tables with keys and constraints and all the stuff we looked at in this class, but the next generation truly is object-oriented databases. So in a nutshell, the reason why it's popular is kind of twofold. The first reason is that it works, the database itself integrates more seamlessly into the object-oriented programming language. So if languages are supporting objects, and we can create a database object, and then we can run methods on that database object, and we can manipulate it as if it were an object in our programming environment, it's a little bit easier to work with it in terms of the development environment. Relational databases, it's always, run a query. As we saw with JDBC, you connect to the database. You have a connection object, and then you have another object that's managing the result set. You have another object that's, doing the database management and all of the other things associated with it. And they're like external objects that are interfacing with the database. So the goal of future development environments and what's actually out there right now and some open source applications that you might find is objects that are true database objects that are accessible from your application, that there's no interface to it. There's no manager, there's no connection or anything. It's just incorporated into the design of the application, which is a lot easier to work with, a lot more streamlined, a lot faster, and we don't have any latency issues or anything like that. So anyway, what we've been looking at is a kind of a short list of some of these applications. GIS systems, very popular right now. Digital publishing systems, putting music, art. If you go online and you just think about all the different apps that you use out there and all the different programs like Google Plus and stuff like that, it's just databases. And most of them are fashioned after object orientation. And they're object-oriented databases that are holding multimedia, pictures, text, forum posts, all sorts of different stuff. And it's a lot easier to work with it from that level. So there's a lot of different applications with it. And we look at, as a couple of examples of these things, computer-aided design, CAD, storing data that is related to mechanical or electrical drawings. A lot of, especially in business fields, a lot of CAD already is integrated into ERP systems and also supply chain management systems where we can automatically generate an order list of parts that you need for a particular manufacturer of something because the CAD drawing is integrated electronically into the database and the information is pulled right out of the CAD drawing. So that's one kind of way of doing it. Another example would be designing for common characteristics. So we can have data that has many different types to it, and then the design of the data can be kind of large, and CAD drawings can be kind of large in general. So in terms of computer-aided design, traditionally the design is not static but evolves over time, and so do objects. If you compare it in terms of object orientation, it grows, it has a life, it has a cycle that it goes through. Updates might be far-reaching, involves version control, configuration management, cooperative engineering, so which makes it kind of a nice advanced level application for object orientation. In terms of computer-aided manufacturing, CAM and CASE tools and things of that nature, This slide set's going to go through each one of those items that we were looking at on the first slide, but I'm not going to go through all of them. I'm just going to kind of summarize it for you. It's used for storing data primarily. In fact, databases traditionally are used for storing data, but it doesn't really do any manipulation on the data. It's a storage and a retrieval technique. So with object orientation, we can do more manipulation. So we can store it, plus we can also have different pieces of information about it, more metadata that's associated with the manufacturer or with the development if we're looking at case tools or something like that. We also have this concept of the network management systems as sort of an advanced database application that exists. So it's coordinating delivery of communication services across computer networks that can be solved by object-oriented databases. Also can be solved by more advanced database applications using storage in terms of objects. So performing such searches on network paths, management, program management, network planning, all sorts of different things can go into the design. And it could also be handled, designed to handle complex data structures and things that require real-time performance and continuous operation, like a network sniffing program or something. Routing, diagnostics, stuff like that can also be incorporated in. What we're seeing a lot of these days is, well, it's mostly related to social media, but office information systems and multimedia systems also lend themselves quite well as an application interface to object-oriented databases because they store data related to computer control of businesses, electronic mail, documents, invoices. You see them all. In fact, most of you probably use these applications on a daily basis. You see them mostly with multimedia, pictures, video, documents. Even Google Docs is a elaborate object-oriented database system, actually, if you think about it. So modern systems now handle free-form text, photographs, diagrams, audio, video sequences, documents that vary in structure. In fact, this is why we have a lot of XML usage these days. XML can be used along with the database to send and receive information, read documents, translate stuff, basically have the computer talk to the computer instead of there being humans involved. We also see, in fact, this is what Oracle is, for the most part, one of the better features of the large binary objects is the ability to store digital media and digital publishing inside of a database. So the support for the large object, for multimedia objects. However, if you do that kind of task with a relational database model, the retrieval of that from a table is very slow. So it's kind of been proven that if I were to compare relational database to object-oriented databases in terms of digital publishing capabilities, no comparison. You can't use a relational database application for that. I mean, database model. So relational database model does not work well for multimedia. It does not work well for digital anything, actually, because the retrieval time is too slow. It doesn't work well with real-time applications. It can be tweaked to work with real-time applications, but it doesn't lend itself because of the data and the size of the data. Imagine having to use a traditional query technique to go through an entire database of information. And you're looking through file by file, and that's going to be way too slow. So in terms of digital publishing, it makes it possible. It makes it more user-friendly and a little bit more advanced to put it into an object-oriented structure. Or, believe it or not, use a hierarchical network or a file system structure for it. Because then you're not looking at the files, you're looking at a directory of the files. And traversing through the files becomes a little easier in terms of trying to navigate. So in terms of digital publishing, becoming possible to store books, journals, papers, articles, electronically, deliver them over the high-speed networks. As in with the Office information systems, digital publishing is also expanded to handle multimedia documents, consisting of audio, video, images. So the amount of information that's available is put online is huge, making the largest database management system has had to manage, essentially. So all of these different advanced database application uses and purposes creates a challenge for the relational database model, long story short. So Now we have a lot of data that's associated with geography. So geographical information systems, where we're storing information. As an example, underwater exploration, land navigation, all sorts of different sources of geographic information. So if you put this in a database and try and search it and use it in an application, it might become a bit of a challenge. Can we keep the volume down for those people who just came in who are disturbing the class right now? Oh, good. See, I thought if I stopped talking, maybe you guys would too. Thank you. Catch him at the break for the attendance that you missed this morning. Okay. It's right, because it's going to be too disturbing. I gave it to you, but it's going to be too disturbing if you go back there right now, because they're disturbing on their own without even going back there. So, all right. So, going back to geographical information systems, searching through and identifying features based on shapes, color, textures, becomes more capable with object orientation. So, last but not least, interactive dynamic websites as well can take advantage of object concepts, considering websites that are online with catalogs of selling clothes, websites maintaining preferences for visitors. Those are actually kind of small little things that can handle no problem with a Microsoft database. Or, in fact, Microsoft Access is used a lot for that. Because you don't want to store cookies on the local client side, and you don't want to store session information sometimes on the server. So instead, if you have a database, you can load the database up with all of the preferences and all of the information, and just do a simple query. And the database isn't really going to have that much information in it, and it's not a critical feature. So if it doesn't load automatically and the preferences don't take place instantly, it's not going to ruin, primarily not going to ruin everybody's user experience. However, you can obtain other things that might be more useful from a database perspective. Shopping cart information, inventory from product catalogs, more advanced kind of retrieval of media, video, things of that nature, where it makes sense to have a more sophisticated database model. In terms of visitors here, modifying, rendering account information, backdrops, I don't know, preferences. So you need to handle multimedia content for interactivity and modifying display for user preferences and user selections. And then also looking at 3D rendering. Can also be done through object orientation instead of relational models as well. So what I've given you in the last couple of slides here, as I've rambled on here, is some examples of some applications for which the database model doesn't work well for in some cases. Like, for example, CAD systems, GIS systems, multimedia, website development. It's kind of a makeshift to see if it actually works and to make it, tweak it so that it works to enhance the user's experience. So this is all drawn to the weaknesses of a relational database management system. And relational database management systems, the strong points of them, highly structured. You can develop, and we saw yesterday, third normal form BCNF tables from design methodologies such as the entity relationship diagramming technique. There's other different normalization techniques. The structure is well known. It's been around for years, very solid. And and you can store a lot of data this way, and you spread it all out into different tables, and you put it all back together with the keys, and it's organized, which is kind of the concept of the relational database management system, as opposed to the hierarchical system, where there's no underlying organizational structure. Instead, the hierarchy is used for the organization. And the hierarchy might be, as an example, a file system. So you're loading things in, but the system, the database management system, has no idea what's in there. The user, when you go navigate through, has to find, and it doesn't lend itself well to a query language like relational database management does. So let's talk about object-oriented databases. No queries again. Instead of using an SQL query on an object-oriented database, you treat it like, and you interface with it like you're programming an object-oriented language. So one of the weaknesses compared to object orientation to relational database is poor representation of real-world entities. The representation of an entity as an object is sort of gone completely from relational models, because now we treat it like, well, we take that entity and we turn it into a table, and we have instances of the entity in the table. But the only way to navigate it is through SQL, which doesn't lend itself well to object orientation and programming. And there's the database, and then there's the interface to the database in order to translate that database to the programming language. So there's a couple of different object-oriented databases out there that are just like programming languages. There are databases that are object-oriented with programming style of interface usage. So you're not, some of them do have query capabilities, but you're not necessarily populating a table and querying the table. You're working in it as if you were programming an object-oriented program and an object-oriented design that fits right in. So it's streamlined into the programming. In fact, you can write the application in the database application in some of these utilities or some of these database management systems. So there's the ability to write the application, the UI to the application, all of the data components to the application, and the database all in one, which is different than designing a relational database and then designing an application to interface with the database. So these are some of the things that make it popular. Normalization in the relational database management leads to relations that do not correspond to entities in the real world. So maybe you figured out from the normalization exercise number 5 that you've done that you're making stuff up, because you took a real world, in that exercise you took a real world, someone's spreadsheet or a dump of data that they were holding from an invoice or something. And you divided it out into tables to put it into a relational database model. And then at one point, in order to get rid of partial dependencies and transitive dependencies, you have to create new tables. They don't exist. You're making this stuff up. In fact, if you didn't create any new tables, then you haven't finished the assignment correctly, because you do have to create some new tables out of that. And you have to decide on your own, what am I going to call them? And what am I, what table is this? And believe it or not, there's actually a couple, maybe there's about 4 or 5 different ways of actually solving that assignment. And the solution I'm going to give you only has one way on it. And the one way I don't really agree with, because it puts stuff in some tables that I would move out into another table. But the concept is let's retain, and the theory is, with normalization, the theory is let's retain the integrity of the original entities. So let's not create it unless we need it, because the more entities we create, the more we split it out, the harder it is to traverse it, the harder it is to actually find what we need, which is why some people don't like BCNF format. They'll like third normal form, but they won't like BCNF because it makes it harder to use the database. So if you take that concept, that's a problem with relational database management systems that object-oriented databases are striving to overcome, to make a better representation of real-world objects. So we have those non-realistic objects that we enter in there. Also, the semantics might be of overloading. As an example, a relational model has only one construct for representing data and the data relationships, which is the relation, the table. That's all we have. All data goes in tables. So the relational model is semantically overloaded. It's everything it fits into a table. Well, how do you know you really want a table? For example, some of those tables that you're making with your normalization exercise don't really need to be tables. In fact, one of the tables might only have a bunch of keys in it. May not even have any data in it. And you're thinking, well, I have to make a table out of this, but it's not storing any data. It's only storing a foreign key and a primary key and another foreign key or something. It's just storing a bunch of keys. But why do I need to do that? In order for the relational model to actually work, you have to make stuff, put it into tables that you're not really storing any data for. It's just there because you need it there. Otherwise, the system doesn't work. So object-oriented databases have strived to overcome that problem as well. Also, poor support for integrity of enterprise constraints. Yeah, it's not an enterprise application. Relational database models are single standalone systems that reside on its own primary server. The database just sits there. It doesn't communicate with anybody else. If you want to communicate with the database, you connect to the server and you connect to the database. No enterprise-wide, no enterprise constraints, no remote objects. So one of the things that Java came up with was, they have JDBC, right? You can't use JDBC on its own. You have to use it with RMI. a remote method invocation or something that's going to support enterprise development. And enterprise development is distributed. We've got this system and this application over here that's connected to the database. And we have this application over here that's connected to the database. Why do we got to do that? And we have latency, all that stuff I talked about in terms of efficiency and making that run more, more streamlined with fewer problems. Well, relational object-oriented databases strives to accomplish that problem by making it an enterprise-wide constraint with an enterprise concept. So you can take and put objects anywhere you want, like Java, as an example, as an object-oriented language with remote object capabilities. So you can treat it like an object, connect to it like an object, and then you can actually create a more enterprise-wide application with constraints that span network and span servers instead of just one single standalone connection point, which makes it a little bit faster, more streamlined. Also, homogeneous data structures. So the relational model assumes both a horizontal and a vertical homogeneity, which means everything's the same. So many of the relational database models now allow binary and large objects. Okay, but that's about it. We have data that's strings and floats and doubles, or dates and times and large binary objects. Well, we can't store anything else. So it's all kind of like consistent in terms of the table by table, but we don't have any ability to flex it out to make it work with anything else. We also have limited operations. So relational database management systems only have a fixed set of operations which cannot be extended. There's absolutely no way to extend a relational database management model. It's structured, it's fixed. So there's no way to modify it to suit it for your needs. Every single relational database model looks the same. Well, some of them don't perform as well as others, but they all have the same structure to them. So there's no extension on the language. So object-oriented databases came around to say, hey, let's provide some extension on the capability, different types of tables, different types of objects or something. And also there's a difficulty in handling recursive queries. In fact, you can't do a recursive query. If you did a recursive query, you'd have to press Control-Alt-Delete or something to get out of it. There's no way of controlling it because there's no language that's being used outside of SQL to perform any interface to the database. So you don't have the capabilities of doing any type of advanced iteration, recursion, control structures. It's not a programming language, it's SQL. So the querying, not so good in terms of, and so we talked about this weekend, PLSQL. You can use that as a procedural language to provide those capabilities in with the relational database model to make it work like a object-oriented database model, essentially, because it's adding programming language capabilities through a procedural language to supplement the SQL capabilities. So long story short, that's also another one of the limitations. So extremely difficult to produce recursive queries. You can, but you're looping it through another support system somehow, another language like PL or something. And an extension proposed to relational algebra to handle this type of query is a unary transitive recursive closure or operation. Well, not done successfully or not done routinely either. It's very difficult to design any type of recursive query with a relational database management system. Here's an example of a recursive query where we've got table A and table B, we have staff number here and we have manager staff number, and we're able to go through and kind of just keep iterating through the same results because we're looking for something, and then in each time we go through we could modify the query perhaps to, I don't know, change what we're looking for, or reduce or add something to change something. So we also have this concept of the impeded mismatches. So most database manipulation languages lack the computational completeness. So to overcome this, SQL can be embedded in a high-level 3GL. So it produces an impedance mismatch, mixing different programming paradigms. So what are we looking at? Data types that don't match. We're looking at dates that need to be converted. Well, this is a problem actually for a lot of people who write SQL queries. You got to take the date that's a string, convert it to a date that is, you know, something that the Oracle system is going to recognize as a date, because that's the date that you have in the column attribute for the domain for that column. And then you use a programming language on top of that. So the goal of a lot of the third-party higher generation 3G, 4G kind of language interfaces, I'd put ODBC in a 3G category, I believe. So is to make it, you know, make a interface driver support to do a little bit better matching between the data that's in the database and the data that's in the application that you're designing. But you still have the ability, or you know, you still have the problem to do conversion. And if you're going to do a conversion, you're always going to get a mismatch. It's never going to be identical, which is why people still like PL/SQL, using PL/SQL, because then you have a one-to-one, and you can actually read the cursory information instead of having to read it from outside, from somebody else's interpretation of the cursory information, which may or may not necessarily be exact. So you never really get an exact match in a relational database model, because you're always pulling it out, using a query to pull out the data, and then you're doing something to the data. So even if it's off by by 1, or you know, by 0.00001 of a rounding, you're still going to have an issue. So
how about using a long instead of the date spots? Forget the.
Well, that's the other thing people do. They go, oh, let's just make it all a string, or let's make it all a long, or just make it all.
Forget about it.
And then you have to worry about, well, what, you know, are you really storing it as what it's supposed to be then? You're makeshifting it, and so every time you pull that out, the problem with not using the correct data types for the columns is that every time you pull it out, every time you write an application to work with it, it causes a problem. So if it's a date and you didn't put it in as a date, then it's going to slow your application. Every single thing that attaches to it is going to slow it down. And it's better just to store it as a date. But in the object-oriented kind of environment, we don't have to convert it. Well, theoretically, you don't necessarily need to convert it. You just use it as what it is, without any type of conversion or interface to it. So we get mismatches, estimated that as much as 30% of the programming effort of code space is expended on this type of conversion. Actually, I would almost make, you know, actually 30% is about right, I guess. So you spend a lot of time, if you're going to work with a database, you spend a lot of time converting the output from the query to something that's going to be compatible with the programming language, because that data is not going to match the data you have. So you got to take this data and make it into that data, which is a lot of conversion, which, you know, I've been pointing out leads to problems, but it also does lead to computational time and efficiency on the program, but it also leads to programming effort. Someone's got to do it. So it's kind of a waste of time in some cases, especially if you can do it automatically. So other problems with relational database models: transactions are generally short-lived, and concurrency control protocols not suited for long-lived transactions. Nope. In fact, what I've been showing you in terms of the transactions and stuff I talked about yesterday in efficiency, connect to the database, do what you have to do, disconnect. Batch it up, do it at night, because you don't want to be connected too long. And you don't want to, why? Because the longer you're connected, the longer you're going to, more highly chance you're going to be disconnected. And if you're disconnected and your transaction doesn't complete, nothing lives. Everything's done at that point, which is what the short-lived concept feels like. You know, you connect to a database and you're there right now, do it right now, do it right now, leave. Because there's no history. So if you design a system that has history to it, then the transactions can be a lot more flexible. And they don't have to happen quickly. And they don't have to, you know, get it while the window's open, get it while it's working. It can actually happen in more real-time fashion at a slower pace. So if we were working with an object-oriented model instead of a relational model, banks wouldn't have to do batch updates at night, because they would be able to do it in real time. It would happen seamlessly, and would probably happen a little bit faster with more reliability to it as well, more instantly. So as applications are advancing and database technology is improving, some of this stuff is happening this way. So not everything's been converted over yet, but we'll always have nightly batch processing just because of the volume of the data. But long story short, other things are posting faster, clearing faster, you're getting faster updates electronically for transactions that are occurring because they can occur and they can happen without there having to be any type of short-lived exposure to that. Schema changes are also difficult. They're very difficult in a relational database model. You can't just go add another table or add another key to a table because all the data that's in there is not going to have that. You know, you're going to have a bunch of nulls. Or you can't just take something out. So it's very difficult to modify the schema, very difficult to extend the model. And relational database models are poor at navigational access. All you got is SQL. That's about it. So you can't navigate it very much outside of SQL. You got only one option there. So kind of poor, low grade. So if you're looking for things, I just actually wrote your paper for you. I just basically completed your 4th assignment for you. So you can go back and listen to this video again. I gave you all of the points already. So there's no excuse why you can't write this paper on your own. Don't cut and paste it. But the paper purpose of assignment number 4 is to compare a hierarchical with relational with object orientation. And hopefully I gave you the impression over the last 10 minutes or so that there are problems with relational model. Those were the problems. So this is lecture number, what is it, 8? I can't remember. I think it was 8. If you want it, it's all outlined there for you. So now what I'm going to do at this point is talk about object-oriented design and object-oriented databases as an improvement to relational database model. So what's wrong with the relational database models? Well, go back and review what I just said. I didn't talk very much about hierarchical because it's not really used anymore. It's an old-fashioned kind of way of storing stuff. And the hierarchical model, as I mentioned before, one of the problems with it is that you don't necessarily know how to query it. It's all by navigation. So if you take a navigational control system, it's a hierarchical system, the user or the person seeking to get something out of this database is self-navigating. You're going through and you're doing a heuristic search through a directory structure, usually by the name of the structure. Same way you use your computer. So that, there's actually, believe it or not, it's kind of a side tangent, but it's actually kind of interesting. There's an object-oriented operating system that works with object-oriented file system that is in beta test. It's an open source kind of utility. I can't remember what it's called right now. It's fast and it's navigation. It takes and creates a better navigational approach, which is kind of interesting. Because if you look at the kind of the trend of desktop systems, I haven't had a chance to explore Windows 8 yet, but you know, outside of the touch control, another interesting part of it, it's more object-oriented than it ever used to be. So everything is associated with objects, which are equivalent to applications. So, which is how, you know, if you think about, you know, the iPhone or Android systems and stuff, although it's object-oriented in user interface design. You're looking at the mail object, you're looking at the web browser object, you're looking at, and then the data that's stored for those objects is related to the object in a method or in a data member kind of fashion. And it's all database supported. So if you take that concept, sophisticate it out into a navigational system, you can actually create a nice operating system based on those concepts, which I believe Windows 8, from what I've been hearing, I haven't tried it out yet, but I believe it's achieving something of that nature. So I'm kind of curious, and I'm going to go check it out myself, but it's supposed to be more object-oriented in terms of the design of the underlying object operating system. So Windows 7, Windows 8, not object-oriented, hierarchical. In fact, you can tell it's hierarchical. It's from the registry. It works off of a registry, which is nothing more than a file system that's keeping track. Actually, it's an index on a file system, and the file system is your file system that we're all used to. But what if you didn't have a file system? You don't get a file system on an Android phone. You don't get a file system on an iPhone. But you have data, tons of data, tons of user music, tons of content. But it's stored in an object-oriented fashion, which is kind of interesting. So anyway, long story short, I think object orientation is going to take over operating systems eventually. We won't have file manager and file explorer and files. What's the sense of files? It's hard to find them. In fact, if you look at any one of your computers right now, you probably don't even know what files you have on them. I can't tell you what files I have on this computer. In fact, the other day I had to bring in another computer because I had the solution files on it. It wasn't on this computer, it was on that computer. It wasn't networked, it wasn't organized. I'm like, where are these files? I know I have them. I just have to go look around. Well, that's user navigated. So if you can build that navigation into a program and make it so it's object-oriented so that you can easily get at this information and it's not just stored all over the place, it's in a centralized repository or something, that would make the navigation easier, more automated. So object-oriented concepts, to talk about that, talks about abstraction, encapsulation, information hiding, objects and attributes. Well, objects are entities, and entities have attributes from our entity relationship diagram. And entities have relationships. Well, objects don't have relationships. Objects have associations and dependencies, which makes it, well, work well for object-oriented databases because we have dependencies in entity relationship diagrams and dependencies that exist, as we've seen with normalization. So we take normalization as a concept and entity relationship diagramming as a kind of a base concept. We can translate that by replacing relationships with dependencies and adding associations and roles and getting rid of responsibilities and adding responsibilities but getting rid of relationships. And then we can actually build the model for object orientation, which is the current, which is what's being done currently in terms of the concept. So we have object identity, methods, messages, classes, subclasses. All these are all the different things that are associated with this concept. And then overloading, polymorphism, and dynamic binding as a concept. So I'm not going to give you a rundown on everything associated with object orientation. Hopefully you guys have some sort of a background on this already if you've done any programming in an object-oriented language. But what I'm going to do is kind of tell you how these concepts relate to databases in terms of the database implementation, because maybe one of these days you'll implement or you'll work with an object-oriented database that's truly object-oriented in terms of its design. So abstraction is the process of identifying essential aspects of the entity and ignoring unimportant properties. One of the problems with entities and entity relationship diagramming is you don't know if all of these attributes are associated with the right entity. Also, one of the problems you're going to have probably on the final is this an entity, or is this an attribute, or is this a relationship? And how am I supposed to figure out which one it's supposed to be? Well, that's where if you add a concept of abstraction into the language and you treat it like an object, then you can clearly identify, and you'll probably have fewer entities or fewer objects, and you can clearly identify the role of the abstraction because it's a more direct relationship with the real world object versus the concept that you're trying to portray via the relationships. So the process of identifying these things and concentrating on what an object is and what it does before deciding how to implement it. So you know you're going to have sales, so you're going to have a sales object. You know you're going to have customers, so here's a customer object. You know you're going to have invoices, you know, and you can just go through and dissect this system out into its objects. We also can incorporate into the object-oriented database design encapsulation and information hiding. We have information hiding automatically when we have private data in an object-oriented language. Well, we have data. So if we take the data that we're storing in a database and make some of it private, some of it public, some of it protected, and go through the entire object-oriented access to it, then we can provide a better information hiding technique. What do I mean by this? Well, let's take HR as an example, human resources. You access your accounting information in the HR table, and there's only one table that's storing all this stuff. Well, they actually can't give you full access to the table, so you have to go through a view concept. If you're designing an HR application and you're going to do it correctly, you're not going to open up that HR table and make it available to the employee. Otherwise, everybody would give themselves a raise or more vacation hours or something, or fix their performance review so it's more positive or something. I don't know. They're going to do something with it. There's no way. There's no constraint on the row. So if the row is available, all the information in the row is available. So there's no protection. So relational database management also lacks security in terms of information hiding. There's no information hiding. So the concept is make a view. So you make a query on the table, save it as a view, pulls out all the sensitive information, all the stuff you don't want to expose to the general public, and then you query the view. So it provides a security mechanism. I talked about this yesterday. So object orientation doesn't have you have to go through and make a view. Instead, it will provide the abstraction for you so that you can make things private, you can make things queryable, not queryable kind of thing. So it provides a little higher level security in terms of being able to define that and what's available. In terms of encapsulation, the object contains both data and the structure and the set of operations used to manipulate the data. So each object can have its own unique instructions and own unique data retrieval. What do you get right now? Nothing. You have select star from this, select this from that. So you can do conditions. You can have a where clause with conditions on it, and you don't have to select everything. But you don't have the ability to say, well, I want this object to act differently, and I want it to do this. I want to tell the HR office, HR object to tell me whose birthday is coming up this month. And well, then you can write a method, put it in the object for the table, and run the method. And then maybe not on the, I'm calling it a table, but it's really an HR object now. Run the method on the object for HR, do that. And I'm going to run a method on the sales object. It says, give me the year-to-date sales totals. So it's not a query, it's a method or an operation that you're running on the data that's stored in the object, just like object orientation, just like if you're doing this in Java. And in the meantime, the object also is storing all the data that's associated. So it's got every single employee from the company is stored in there too, which is nice. Because then you can say, well, give me all the data. Give me all the instances of all these objects that live at this company or that are created by this object, that are members of this object type. And then you can take an object type that's, let's say, for example, that's an HR object type, and say, well, we're going to promote you now. We're going to make you, instead of a programmer, we're going to make you assistant vice president of the organization. Then you can convert the instance of the object and convert it into a VP object instead of a programmer object. You can't do that with a relational database model. What can you do with a relational database model? Change a value, change an attribute, and it's going to be called job title. So now they're no programmers, so change it to this. So, but your tree is still the same. It's not having any new attributes. It's not having any new operations or anything associated with it. It's still the same thing. You're just changing the attribute. So it's not really encapsulated correctly. There's no encapsulated data. There's a table. It's almost like a spreadsheet if you think about it. But you're navigating the spreadsheet through SQL instead of using, I don't know, a spreadsheet program. So anyway, long story short, there's no encapsulation in a relational model. But you can add it, and you can actually make it so that the vice president model is a different object type than the programming model. Also, the information hiding, separating out the external aspects of the object from the internal details as well, which are hidden from outside. So you can have the payroll and have all the sensitive information hidden for the object, so it's not accessible. And then it allows internal details of an object to be changed without affecting the application that's using it as well. If you change the structure of your table and you have an application that's running a data set on that table, your application is going to go out the window. You can't just swap out that table with another. Well, you can swap the table out with another table, but it has to be called the same thing. It has to have the same row, same column, titles and attributes and data types. It has to be identical. Well, you have a little bit more flexibility with object-oriented environment, more extendability, and provides data independence as well. So that the data itself can be stored independent of the object itself as well. So the object is an entity, as I mentioned before. It's the same thing. A uniquely identifiable entity that contains both attributes and describes the state of the real-world object and the actions that are associated with it. And by the definition is very similar to the definition of an entity in entity relationship diagramming. We know the entity is the relation is another word for table, which is how that kind of fits together. However, objects encapsulate both state and behaviors, and entities only model state. So we don't have behaviors in entities, but we have them in objects. So it makes sense to use an object instead of an entity so we can capture the behaviors. What's the behavior? Get promoted, get demoted, I don't know, print out year-to-date sales, all sorts of stuff that can come out in terms of operations. Okay, so we all know about attributes because attributes are the columns that end up in the tables on an entity when we diagram those out. Attributes mean the same thing, contains correct state of an object, however. So it's not necessarily, it's more state-oriented in objects, not necessarily attributes in terms of column. There's no column association with that. Instead, it's a state in an object-oriented database. So attributes can be classified as simple or complex. Isn't that kind of like complex or compound or, you know, like an address in the attribute world of an entity? And composites, attributes where we've got attributes that are composites. So address is, you know, street, zip code, city, state, area code, you know, like phone number is an abstract composite attribute, composite keys, composite attribute. Anything composite is artificial because it's really a combination of a couple of attributes that we're calling a grouping. Well, we don't actually have to worry about the grouping because it's not going to necessarily be associated. It's going to be instead it's going to be a state association with a single attribute. So it's a little bit easier to kind of abstract out. So let's see. Simple attributes can be primitive types such as integers, floats. Complex attributes can contain any other reference. And reference attributes represent relationships. So if you take reference attributes and think about the concept, inside of my, let's say I've got a sales object, and the sales object is like the sales table. And inside the sales object, I have inventory items. Why don't I just stick the inventory item, this inventory object, inside of? So you know how we can put objects inside of objects? We can have a date object, an inventory object. We can compound the objects, nest the objects together. Then we don't do a query. Instead, we already have the connection. We already have the relationship. So we put an instance of the hammer and the nails and the glue or whatever we're putting on the sales receipt. We make instances of those from the inventory objects, and then we have them already inside of the other object. There's no query, there's no relationship, they're already connected. So you form the hierarchy of the objects. So when you print out the sales receipt, it already has in it access to the real object. It's not a copy of that object. It's not information taken from that. It's the object. So you can get everything from its truest form, which makes it more reliable, more up-to-date, and more real-time, versus a copy and a paste or a movement from one table to another table. Because usually when we create tables that represent sales information, as an example, or sales receipt, if we're going to do it this way, we're copying information from one table and we're putting it into another table. We're creating redundant data. So in some aspects, using the attributes correctly and nesting the objects in an object-oriented design removes the redundant data. Because there is no redundant data because we don't have keys. There's no such thing. In an object-oriented databases, we don't have primary and foreign keys and stuff like that. That's relational. So instead, we just nest the objects, and so we don't have redundant data. So remember yesterday I called it controlled redundancy? It's still redundancy. It's just put in there for control reasons. So we take out uncontrolled redundancy, we put in controlled redundancy. So object orientation just takes out redundancy 100%. So there's another thing you could have put in your paper, or you can put in your paper if you're still writing it. It removes redundancy issues. It also removes inconsistencies just naturally. If we don't have it in more than one space, why would we have inconsistencies? So the whole relational model is flawed if you think about it in terms of, you know, it just lends itself to problems. It makes it so that you can put redundancy in there that's not controlled. You can put inconsistencies in there. You can have data that doesn't work and can have a bad database design. So in some ways, the object-oriented model creates a better design. So, all right, complex attributes can contain collections and references, and then reference attributes represent relationships, and then an object can contain one or more complex attributes. It might be called a complex object. So we have different types of objects that we might actually create. We also have object identity by an identifier. So object identifier, OID, is assigned to an object when it is created. So if we use an object numbering system or an ID system, then it's like a table name, if you think about it. How do we identify tables? We give them names. And so when we say the customer table, the sales table. So it's the same concept, but it's an identifier for the object. And then we can use the identifier for the object for access purposes, control purposes, who owns this object ID. And we can organize. In fact, Oracle actually uses an object ID process already. If you've looked at some of the object-oriented interfaces to building the relational model inside of Oracle, everybody has an object. So every user is assigned an object ID of their ownership of their user object. Inside of their user object, you have the tables, the views, the indexes, and everything, which is how we get that references that goes on. It says, you know, user 1 dot table name dot something. It's all referenced by object, but the model, the relational model, is still retained inside of the object, but the interface to the model is object-oriented these days. So, all right, so system generated, unique to that object, it's invariant, doesn't change, and it's independent of the value of its attributes, that is, its states. Invisible to the user, ideally. Wow, yeah. It is sort of, because the user, it's almost like a memory address. The user doesn't actually see the cursor either, so we're not going to see information like that. So object identity in terms of its implementation. In a relational database model, object identity is a value-based. So we have primary key that is used to provide uniqueness. So it's a value-based, and if we treat each one of the rows as a separate instances of those objects, we're getting at the rows or those instances by a key value, primary key. So primary keys do not provide the type of object identity required for object-oriented systems. So it doesn't provide the type of access that's needed. So instead we use an object ID that gives us our unique object, or its name, or identity. So keys only are unique within the relation, not accessed throughout the entire system. So we can have first name over here, and we can have first name over there. We can have student ID over here, student ID over there. So key generally chosen from attributes that are used in there, making it a dependent on the object state. So while the instance of that object is in there, the ID is in there, otherwise we don't have access to that row anymore. Which happens all the time. Actually, you remove it, so then the database gives you an error and says, hey, you can't remove this row. It's being used in another one. You can't remove a primary key when it is being referenced by a foreign key in another table. Databases won't let you do that because it ruins the integrity of it. It ruins the key constraints, or violates the key constraints, I should say. So object identity, in terms of its implementation, programming languages use variable names and pointers to virtual addresses, which comprise of object identity. So in C++, object identity is the physical address in the process memory, which is too small, scalable, requires object IDs that are valid across storage volumes, possibly more different computers. If you make the object ID sort of like the remote, the RMI engine, which is, if you've looked at RMI, or you look at some of the servlet, or some, even so, it's all managed by objects, and the objects keep a global dictionary or a global lookup table of all of the IDs of all of the objects. If you centrally manage it like that, instead of having the object be responsible for its own ID, then you can make a distributed system out of it. And so you can have an object-oriented database that spans multiple systems, and the objects are located on multiple servers all over the place, which makes it a little bit more flexible, and it provides the enterprise-wide. And you can't do this, you seriously can't do this with a relational model, but you could do it with an object-oriented model. So further, when the object is deleted, the memory is reused, which may cause problems depending upon the situation as well. So advantages of using an object ID or a global object ID tracking system. They're efficient, they're fast, they can't be modified by the user, and they are independent of the content. So we can create a managing system for it that the user is impossible, but the user can't delete something that's going to violate a constraint. And we don't have to warn the user about anything. Okay, so objects have attributes. They also have methods or messages or functions, functionality, or operations, depending upon how you like to use the word. Method defines the behavior of an object. So it's a set of encapsulated functions, which is where that function comes from. And then we have messages. Messages are sent back and forth between objects. So they request one object of another, asking it to do something, to execute one of its methods, or to perform something. So here's our object showing the attributes and the methods. We have method 1, method 2, 3, 4, and all of the, this is kind of a weird picture actually, because I don't know why people imagine objects as being circles, but and yes, it's weird because I never really thought until I started looking, back when I was studying this stuff, I was like, why are entities square? I could never get past that. I always thought an entity was a circle. And I don't know how do objects end up being circles? I don't know. I think objects are sort of rectangular now, but entities are rectangular. So anyway, here's an object circle. So objects is like, start trying to ask, what does an object look like? I don't know. It's a circle. So here's a circle object with some attributes in the middle. Why are the attributes in the middle? I don't know. The state of the objects. Here's an example of a method. If you've never seen one before, it's not even valid syntax. It says method void update salary. Anyway, it just has some functionality in there. Most object-oriented programming languages use the implementation of a class to create an object. So class, by definition, is a blueprint of defining a set of similar objects. So if we were writing an object-oriented database and we were going to design that, it would make sense to use a class. Just like we could, use an SQL statement to go create table students and define all the attributes. Well, probably not a bad idea to use a class as the underlying model, and then you can have many different objects that are created that follow the class template. And then you can even build in the concept of hierarchical relationships and inheritance and abstraction, abstract classes and interfaces and inheritance. And yes, there are object-oriented databases out there that follow this pattern 100%. And that's one of the methods that's being used for this. So objects is a class. They're called instances, objects that are made of the class. And then the class is also an object of its own class attributes or class methods. So if you use this model, then you can have class and instance level attributes and methods, which makes it possible. So here's an example of a class instance sharing attributes and methods, and this is a branch object representing a branch. And then we have branch number 1, 2, 3. So if you remember the entity relationship diagrams I gave you in the beginning, it was a couple months ago, or about a month ago, we had branch and branch office. This actually comes out of the same textbook, and it's the object-oriented version of the entity relationship relational model. So this is an object now. And remember before I said, you can draw your entities and you can put your attributes inside of your entities. If you do that, instead of putting out little bubbles on the outside. If you do that, here's your attributes right here. And then underneath it, you've got your methods. You don't have methods in an entity relationship diagram. No methods at all. But this would be an object diagram. An object diagram showing the same thing as an entity relationship diagram would include this information. So we can still model the database design using an entity approach. But rather than entities, we're using objects. And if we're going to use objects, we're going to model the attributes and the methods. And then we're going to show instances of objects that might exist. We don't have to, but we could just show this part here and say, well, that's one of our objects that we're going to create for this program. So we have the subclasses, superclasses, and inheritance that's associated with this concept. And inheritance allows one class of objects to define a special case or a more general case. Just the same it does in programming languages. So special cases of subclasses are more general than the superclasses. So subclasses, superclasses, and then the concept of generalization and specialization, which you get from object-oriented programming, applies as well. So subclasses inherit all the properties of the superclass, and they can also define their own unique properties. So subclasses can redefine inherited methods as well. Which brings up the point of overloading and overwriting. So you can't overload or overwrite tables in an entity relationship diagram or in a relational database model for that matter. A table is a table. You can't subclass a table either. And you can't change a table, modify it for your particular purposes. You can if it's an object. So think about the concept in terms of what you're familiar with from a programming perspective. Take that and apply it to a database model. A lot more flexibility, a lot more ability not to have to reinvent the wheel. So it promotes reuse in the database model. So object orientation also supports a reuse of tables without having to drop the table, truncate the table, recreate the table if you want to change it, modify the table. So much of relational database management, what does a DBA do most of the time? Take data out of a table, recreate a table, put the data back into the table, fix the table, do all this stuff. There's no hierarchy. It's a standalone table. The table changes, the table changes. So if you take it and translate that into object orientation and create inheritance with overloading and overriding, you could fix the table by overloading it. So you can overload the table and you have a new object that has the new feature that you need, that you've added, you've supplemented something to it, or you've changed the behavior to meet some sort of purpose it needed. So there's less rework, more extension and reusability as you build the database to go through all the different transactions, all the different things that happen in the company throughout the years that cause databases to have to be rebuilt. So what I'm leading to is the life of the database. If you build it in an object-oriented model, it's going to last longer. Not only do the transactions last longer, could last longer, they're not quite as short-lived, the database isn't as short-lived either. What are we doing with databases today? We're keeping them for years and years and years, and then someone came around and said, what about a data warehouse? We can take all those databases and stick them together. Well, if you created an object-oriented model out of it, you can actually have the data warehouse integrated into the model, and so your data would just grow, and then you could object it, essentially extend it through behaviors of other objects from other databases, and you'd have a more robust, long-term, long-lived warehouse eventually. So some experimentation's been done with warehousing applications to translate that into an object-oriented world to make it more extendable, so you can automatically create warehouses without actually even having to do anything really work-wise. In fact, it would be, hopefully it would be in future generations automatically created by people who are supplementing it with their own object-oriented databases. So you basically connect all the object-oriented databases together, call it a warehouse. There you go. So the hierarchy is actually created already. Associating the superclasses, the subclasses, and inheritance associated with object-oriented databases. All instances of subclasses are also instances of superclasses. So the principles of substitutability, swapping out one object for another in instances of classes, can be whenever a method or construct expects an instance of a superclass. So when I teach object orientation, I call it upcasting. So you can upcast or downcast, which means take an object and turn it into another object because it is of the same object category, same object type, which means you have a lot more flexibility in your ability to use the objects. And the relationships between the subclasses and the classes also has a kind of relationship. In object-oriented language, they call that an ISA relationship. So it's a kind of or ISA. This is an object of this, which is an object of that. So we have also 4 types of inheritance: single, multiple, repeated, and selective inheritance as a concept. So here's an example of a single inheritance with a person, and the person has a subclass of staff, which is also a person, and then we have a manager and a sales staff, which is also a staff, which is also a person. And then a multiple line inheritance where we have a manager and a sales staff, which is part of the sales staff model. And then repeated inheritance, where we have a sales manager that's a manager and a sales staff, and it's also a staff person. So you can have a circular where we can't get this in a relational model. So in terms of overloading and overriding and polymorphism as it's applied to object-oriented databases, overriding, process of redefining a property within a subclass. We also have overloading, which allows the name of the method to be reused in the subclass or across different classes. And then there's also the concept of polymorphism, which means many forms. So we have 3 types: operational, inclusion, and parametric. So we can apply them in terms of the context. Examples of overriding. So we might define a method in staff class to increment the salary based on a commission. So the method void give commission would be an operation. So we can automatically run operations on the objects that are representing the tables. And for everybody who's an instance of that, increment them. So at the end of the year, when a cost of living index is approved and everyone gets a 1% raise, you can automatically do it on the object, and everybody in the database gets a 1% raise. It's a little bit different functionality, a little bit different thinking than running a query and doing an update. And you may wish to also perform different calculations on commissions for the manager subclass as well. So you have a lot of flexibility in terms of how you're going to override or overload methods. And this is just a couple of examples. This is using C, or actually C++, using printf. Actually, it's a method written in C, but it's theoretically C++ because C doesn't support object orientation. So we also have the concept of dynamic binding. So dynamic binding works with a runtime process that's selecting the appropriate method based on the object type. So if we have an object-oriented database and we want to print something, as an example, we can run a print method. And in terms of the dynamic binding, it would print out correctly, whether it was a person object or a salesperson object or an invoice object or a company object. So depending upon what the object was, it would figure out how it's supposed to print itself. Can't do that with an SQL query. With an SQL query, you have to get the information from a query. You have to know the column names. You have to know the structure of the table in order to actually perform that query. And then when you get it back, you have to actually, manually print it out or manually do something with it. There's no functionality associated with that either. So with a list consisting of an attribute name and objects from the staff hierarchy, you can write list I, print. So you're running a method on, let's say, an array of objects that are being stored. So it makes it more generic, so you can apply multiple functionalities to the same or different objects. In terms of the complex objects, the objects consist of sub-objects, so you don't have any keys anymore. So instead of putting the instead of putting the student ID, as an example, into every one of the tables, you just stick the student object into every one of the tables, or every one of the other objects that's going to use a student object. So you have complex object in that case, because you have an object that contains another object. So records, student registration, would actually include the instance of, a linkage basically to the instance of the object. And you wouldn't actually have to copy any data in there. And if the instance of the object changed, well, it would also change for the registration table as well. So there's no updating. It's automatically synced correctly in terms of this concept. And so we have the is a part of or is a relationship that is maintained. And then we contain an object that can have it encapsulated within another object, accessing another complex objects method as well. Or have it as an independent existence and only have an object ID that is stored in the object, which is more like a reference or a pointer, actually. So storing objects in relational databases. So one approach is achieved by persisting with an object-oriented programming language. So it's to use the relational database management system as the underlying storage engine. This is what Oracle supports, actually. Oracle is a relational database model, but you can store objects inside of the database. So it supports the concept. Requires mapping of a class instance, i.e. an object, to one or more rows distributed over one or more relations. It actually just takes and physically stores the object. So instead of the data type being a string or an integer, it's a large binary object. And if it is, then it can store anything that would support it up to the file size limitation of, I think, about 4 gigs actually, which is pretty big. So to handle a class hierarchy, you can have 2 basic tasks being performed. You can design a relationship to represent class hierarchies, or you can design how objects will be accessed through the hierarchy, and depending upon how you're going to design a hierarchy, if you're going to work with that. So. And here's sort of a hierarchy this is sort of like a entity relationship diagram. Actually it is, but it's an object diagram. with the attributes inside of it. So the manager, the salesperson, and the secretary are all staff. So they have a mandatory participation with staff. So mapping classes to relations. So there's a number of strategies out there for mapping it, and it results in a loss of semantic information. So we can work forward from a relational database model. We could probably work forward into an object-oriented model. One of the problems with object orientation in terms of a database model is you can't work backwards. You can't take the object and map it back to the table, to the relational table. So it's an all or nothing if you're going to take this route, essentially. You can map each one of the classes or the subclasses to a relation, but you're going to miss a lot of the subclassing, and you're going to miss the hierarchy and all of the other things that object orientation adds to it. If you were to move things backwards, that particular example here looks like here with a staff, manager, sales personnel, and secretary tables that could be created from that. You can also map each one of the subclasses into a relation, and then you can map the hierarchy into a single relation as well. What you end up with is more relations. So what do you get with relational databases when you start creating an entity relationship diagram? You get an initial set, you start normalizing it, you get more relations. So the same thing actually happens when you go from object orientation back to relational models. You end up with a lot more tables than you would normally think of, actually. So the next generation of database systems. We have the first generation of the database systems, and this is kind of my review cap here, which was the network or the hierarchical. And this is what you're writing the paper on, by the way. It requires complex programs or even simple queries. For everything, it requires a lot of work. And you have minimal data independence and no widely accepted theoretical foundation. So these are some of the things that are associated with the network or the hierarchical model. If you move into the second generation, and yes, relational database is second generation, it helps overcome some of the problems. The third generation, or the object-oriented database management systems, do what I've been talking about for the last, I don't know, 45 minutes or so in terms of object orientation. It accomplishes a lot better in terms of the basic usage of the data, the storage of the data, and the manipulation of it. So here's the history of the data models themselves. The hierarchical actually came before the network, but these are actually sort of grouped together these days. So a hierarchical or networked is pretty much talking about this level. The relational that came, started, and we had the relational entity relational model that kind of improved it, and the semantic data models that came out of that, and then now this is where we're getting the object-oriented models that are coming from that. So in terms of the data model itself, has to, in order to put, and this is another little tidbit of information, in order to actually classify your database as an object-oriented database and put it into this model, at a minimum, it has to provide database functionality, and it has to support object identity, and it must also provide encapsulation, and it has to support objects of complex state. And complex state means that it includes other objects. So that's where the keys are coming into place. So foreign key, primary keys, all the key constraints get turned into complex objects. So we have multiple objects that are nested inside of other objects. And here's the origins of the object-oriented database model with all of the components that are part of it. This is actually slide number 49. It's actually kind of a recap of all of the things that I actually talked about. So, of the different components or characteristics of an object that is part of a object-oriented database model. So we have persistent programming languages that are being used in terms of a model to model the object-oriented database model. So these languages that provide users with the ability to transparently preserve data across successive executions of a program and even allow the data to be used at many different programs together. So in contrast, the database programming language, the SQL differs by its incorporation of features beyond the persistence, such as transaction management, concurrency control, and recovery. So in terms of representing SQL, it is a persistent programming language. However, it also supports database features for commit, rollback, describe, and that's where you get, implementations of SQL Plus, which is the extra Oracle features that are associated with the language as well. The concept of the persistent programming language, however, eliminates the impedance mismatch by extending the programming languages with database capabilities. So we have new languages that are coming out that are going to work in replacement of SQL that work with object-oriented databases, because you can't use SQL with object-oriented databases because we don't have keys anymore and we don't have the same kind of table lookup. So the other component, in order for this to become the mainstream in the current generation, is to work on the capabilities of the persistent programming languages, to decide which language is going to be used, or come up with a new language, and support not only data definition, but data manipulation and object creation in this language. So languages themselves are language type systems that model data containing rich structures and mechanisms for the modeling. So in some of the first class objects are treated like any other object in current programming, persistent programming languages. So we have to extend it sort of to make it more flexible in terms of its support, and make it so that we can use procedures for all sorts of different data types and different things that we want to create. So the rest, let me just see what's in here actually. Let's see. I don't normally cover anything past about single level versus two level storage models and storage systems. In this particular lecture, I'm trying to think, probably if you can keep the volume down over in the left-hand side of the room. You're starting to sound louder than me, and I have a mic. You have about 10 minutes left if you can just hold off the conversations for about 10 more minutes. Then I don't have to feel like I'm talking over you or competing with you. Did you hear what I just said? Okay, thank you. It's okay, it's just distracting. It's kind of rude, actually, too. Okay, so what do we got going on here? I'm going to end in about 10 minutes. I'm going to stop at this point, which means for your paper purposes, and the reason why I'm giving you this lecture is to give you some ideas about what you want to write about when you do your comparison between hierarchical, relational, and object orientation. This lecture is a good resource for that. It does stop, however, at around slide 57. And what I want to do is kind of conclude the concepts. I don't really want to get into persistent languages, but I want to conclude the concepts with the possibility of this. Not only do we have to come up with a language that has to be used, and the language category falls into the persistent programming language category. It's not an object-oriented language, which is interesting. So we can create an object-oriented database, and this is where some of the experimental systems have sort of differed with what's on the market right now. If you do an internet search, you will find object-oriented databases. There's a ton of them out there right now, and they're all a little bit different. Some of them are actually written in and manipulated through an object-oriented interface, but you don't have to. You can actually create what's called a persistent programming language interface to create the data model, to create the objects and manipulate it without using an object-oriented environment. So we have some that are on the market that are following that trend, and then we have some that are following a more traditional programming implementation, which is interesting because it kind of changes the DBMS, traditional DBMS perspective. So DBMS, Database Management System, is what we're calling Oracle. It's what we're calling MySQL. It's the program written to manipulate, to create the objects, to create the tables and the structure, right, of the database. But it's not written in an object-oriented language. It's not written in a procedural language either. In fact, it's like most of this stuff is GUI-based. In fact, the tools today outside of SQL is all GUI. You drag and drop, and here's another table, and here's another table, depending upon the interface you're using. So you can take some classes and learn Oracle in terms of how to drag and drop, or how to use SQL to create tables. It doesn't do very much good, however, because all that stuff's going to change. In fact, it's changing already. We have different tool sets, and then we have different third-party tools that you can do, like PHP admin as a great example, to create. You can manage your entire database using PHP admin. So you're using a PHP script to do it. Problem now and now maybe you can kind of get where I'm coming from here. The problem with object-oriented database models is we have to create yet another type of interface to it. You can't use PHP admin for that. It's not going to work. So what we have now is a bunch of tools that are coming out. Some of them are written in persistent programming languages. Some of them are written in Java. Some of them are written in C++, where you're designing and you're creating your database using this interface or this program that's turning into the database management system. So we'll still have database management systems as a concept, but it'll be a different type of program because you're creating a different type of database and you're not creating a relational table anymore. So the other characteristic to this is the concept of the storage model. So Oracle uses multiple drives with a table space, and you can put extents and stuff on the drives, and they have their own proprietary kind of storage model. Well, so does MySQL, so does Microsoft Access, so does every other database out there. So another thing that you'll find is differences between object-oriented databases is the storage model. We have single-level, multi-level storage models, where we have in traditional programming languages that lack the support for many of the database features. We can add them in on an object-oriented model. We can increase the number of applications that require functionality from database systems and programming languages. We can create a new storage model that's going to structure the data for us. And so if you read through and look at this, you'll see the differences between the single and the two-level. And this is just an example. It's not necessarily what will be or what is implemented. It's basically looking at the traditional database management system and how the programmer has to decide to do everything. In fact, even with Oracle, the programmer has to decide how big to make the extents, how big to make the storage space, how much storage space they're going to use, how many objects they're going to use, and type checking and all of the other little things that might come around with it. So the rest of this lecture gets into different schemes for storage models. So I'm not going to cover this because it's way above and beyond the concepts that I was presenting in terms of a comparison between the different hierarchical, relational, and object-oriented models. However, you might find this interesting in terms of the comparison between the relational and the object-oriented storage models. There's different techniques that are being used to kind of create a higher, more sophisticated storage model, essentially. Because databases themselves are highly dependent upon their storage capabilities. I mean, with the value of the database is its ability to store data and to keep it long term. So if you optimize the storage model, then you're making it the accessibility to it faster, more reliable. You're basically using a lot of more optimization in terms of that. So you can optionally read through the rest of this. That starts at around slide number. Here we go. Around slide number 55 to the end of it. It's kind of sort of optional reading. It's not going to help you with the fourth assignment. It's not going to help you at all, actually. So, but you can definitely find it interesting. Probably, I don't know. It'll also go through the Oracle model, client-server architectures. There's a lot of extra stuff in here. It's going to go over advantages and disadvantages in terms of the different storage techniques as well. But in terms of object-oriented, it's just I'm concluding here with this end of the slide, so I've sort of skipped the data model itself. But to sort of include in terms of advantages and disadvantages, you may use this information as well in your fourth assignment for the comparison. Looking at, and I've actually gone through all of these already, so I'm not going to recap it, but it gives you some more ideas in terms of the comparison. And, the rest of this is actually going to review. If you're interested and if you've missed any of the entity relationship diagramming stuff, the rest of this lecture actually goes through the different relationships and hierarchies and stuff. And it actually compares it to object orientation, which is kind of interesting as well. But it kind of goes way and above and beyond what it is you need for this class. So, questions before I end this lecture? Because you guys all love to talk today. No? All right, let me end this recording then as well.